Welcome to This Explainer. So if you've ever stared down a complex math problem and thought, man, this looks like an alien language, well, you're not entirely wrong. But today we're going to totally reframe how we look at mathematics. Let's ditch the idea that math is just this tedious chore of memorizing formulas or some frustrating hurdle you just have to get over. Instead, we're going to look at it for what it truly is, the literal language of the cosmos. Seriously, everything around us, from the giant spirals of galaxies to the way branches grow on the trees in your backyard, it all follows a structural code. By the end of our time together, you'll see that learning math is really just learning how to translate the universe itself.
Okay, let's dive into this. Kevin Lamaspaspos perfectly captures the high stakes here when he says, scientists use math to tell what time it is or to measure how far exactly a star is. That is why it is called universal, because it can be used in a lot of ways. I mean, think about that for a second. We aren't just talking about balancing a checkbook or figuring out a tip at a restaurant, though, hey, math does that too. We're talking about a tool so incredibly versatile that it can stretch across the unimaginably vast distances of space to measure a star, and then zoom right back down to operate at the microscopic level. It's literally the only language we have that completely transcends human borders, cultures, and honestly, even planets.
Which brings us to a really fascinating question. We know math is the universal code, but how exactly do we speak it? Think about it. If you were suddenly dropped into a totally foreign country, you'd need a dictionary, right? A grammar guide. Some way to translate their words into concepts you actually understand. Well, to speak the universe's native tongue, we need a mathematical Rosetta Stone. We need to figure out the syntax, the vocabulary, and the rules of engagement. So let's start translating.
Section 1. English versus mathematical language.
And this brilliantly illustrates where our translation journey begins. It really helps to compare this new mathematical language to one we already know. Now, English is beautiful, but come on, it's full of confusing exceptions, like I before E except after C, unless, you're a weird neighbor. Mathematics, on the other hand, has a distinct, perfectly logical alphabet. Instead of A, B, and C, math uses symbols and operators. You've got your standard digits, sure, but you also have symbols that represent addition, subtraction, equality, infinity, and even really specific concepts like pi. These symbols form the absolute foundational vocabulary of our universal language. They let mathematicians take incredibly complex, totally abstract thoughts and represent them in this really compact visual way.
So the language of mathematics actually improves upon our clunky everyday language by sticking to 3 core characteristics. First up, it's perfectly precise. Think of the 4 basic operations: addition, subtraction, multiplication, and division. There is absolutely no guesswork here. 2 plus 3 equals 5 every single time. Second, it's highly concise. Instead of writing out a massive, rambling paragraph to describe a geometric relationship, we just use appropriate shorthand notation that gets straight to the point. And third, it's incredibly powerful. Because it's so precise and concise, this language is capable of solving ridiculously complex problems and analyzing concepts across vastly different fields, from quantum physics all the way to computer science.
Let's move to and see how this builds into everyday practice, because the differences are stark. Everyday English is super subjective, right? The exact same sentence can be interpreted in 5 totally different ways depending on who's listening. Mathematics completely eliminates that ambiguity by using standardized conventions. A perfect example is the order of operations, which you probably remember as PEMDAS or BODMAS. Whether you're sitting in a coffee shop in Tokyo, an office in New York, or literally on a space station orbiting Earth, if you see an equation, you know exactly what to do. You evaluate the parentheses first, then the exponents, followed by multiplication, division, addition, and subtraction from left to right. This universally agreed upon convention ensures that absolutely no one gets confused when translating the code.
Section 2. Expressions and equations.
All right, now that we've got a handle on the basic vocabulary, we can transition to the next linguistic level. We're moving from single words to mathematical phrases. Let's start with a mathematical expression. By definition, this is a combination of numbers, variables, and operators that represent a mathematical value or relationship. If math symbols are our words, then an expression is a phrase. It represents a concept, but it doesn't make a complete statement all on its own. For instance, the formula for the area of a circle, pi r squared, that's an expression. The left side of the Pythagorean theorem, a squared plus b squared, also an expression. They're basically fragments of thought, just waiting to be completed.
So the crucial point is understanding what happens when we finalize that thought. 2 plus 3 is a mathematical expression. It's just a phrase, but y equals 2x plus 3 is a mathematical equation. By introducing that equal sign, we're basically adding a verb to our sentence. We're asserting that a specific relationship is true. So the expression is just the idea, but the equation is the complete declarative mathematical sentence. In this specific case, y equals 2x plus 3 is a complete sentence that perfectly describes the trajectory of a straight line. Makes sense, right?
Section 3. Relations and functions. Okay, so we've covered our vocabulary, our phrases, and our sentences. Now we move to the conversations actually happening within the data. In mathematics, a relation is defined as a set of ordered pairs from a domain, which is your input, and a range, which is your output. Put simply, a relation is a specific connection between two sets of data. Imagine two groups of people, and you're mapping out who is friends with whom. That map? That's a relation. It defines exactly how the elements from one set interact with the elements of another. Often, mathematicians will use what's called a function to represent this relation, applying a very strict rule to how that output is assigned to each and every input.
Now, what's really interesting about this breakdown is how systematically we can analyze the 4 grammatical ways this data can relate to each other. It's essentially the relationship status of our numbers. First, we have one-to-one, where each input connects to exactly one unique output, a perfect exclusive pairing. Then we have many-to-one, where several different inputs all point to the exact same output. Next up is one-to-many, where a single input branches out to connect with multiple different outputs. And finally, many-to-many, which is this complex web where multiple inputs relate to multiple outputs. By understanding these 4 relation types, you can map out and translate almost any complex interaction in the natural world. I mean, everything from tracking social network connections to predicting global economic trends.
We started off looking at math as a universal language. And hopefully you can now really see the grammar that holds the whole shebang together. You've got your symbols as your alphabet, expressions as your phrases, equations as your complete declarative sentences, and relations as the complex conversations between data points. You now possess the Rosetta Stone. The rules are standardized, they're precise, and they are absolutely incredibly powerful. So I leave you with this question. If math is literally the universe's native tongue, what are you going to translate next? Thanks for joining me on this explainer, and keep exploring.